what is the real reason to study this? Is to study rational curves in X. And I mean, we have already some tool to study that. Esempio Taylor scheme, no? Scheme. So why to introduce the moduli space? Space M bar. Zero and X. So we already have the Taylor scheme, and we are introducing a new tool that is this one, which have a very not so, how can I say, intuitive definition. I introduce maps. So why we study this since we have already that? Well, the reason is that this is generically better behaved than the inverse scheme. So this is one of the first of our advances. What this has better than the other one. So the first one is it's better behaved, and we will give an example later. Second one is it has a recursive structure. Which the Hilbert scheme doesn't have. Today we will see these two facts. We will try to explain why this is true. Well, the Hilbert scheme is not junk. It has some advances. For example, it parameterizes curves. What I mean that the Hilbert scheme, you know what's the Hilbert scheme? You have a polynomial pt. In the case of curve, is 1 degree polynomial, so it's something like dt plus d plus 1. It's something like that, where G is the genus and D is the degree. It should be something like that. And you parameterize all objects with this fixed Hilbert polynomial of X, where X is a polarized variety. So we have a very ample line bundle fixed on X, and we study all this subject. So this subject really parameterize curves. So it parameterizes really the object you want to study. This doesn't. This parameterize maps to curves. So it's indirect, and this sometimes can give problems. So it's not direct. But we have these two facts, and today we are going to see that. See why this is. Okay, let's start. Okay, as I promised today, since today, we will focus only in the case of genus 0, because is the best behaved is when you start to understand the cases of higher genus, which is far more complicated. And it has given us a lot of successes. We solve a lot of enumerative problems, classical and not classical, using this case. There is some case where also curves of positive genus have been solved just looking at the case of genus 0. Maybe if there is time, we will see this example later. So let's start. Notable subsets. Again, X is a projective smooth variety. Beta is the class of the homological class of a curve. N is an integer. We studied the case of genus 0. Okay. The first one is this without this bar. And this parameterized, this is the open, non-empty subset parameter regime maps with irreducible domain. So when the domain is P1, two M star 0 n x beta. So, I mean the sum of this, and we add the star. And this subset the subset parameterizing maps free of automorphism. What does it mean? So the first one is just this. So, with irreducible domain. The second one is curve without automorphism. When can I have an automorphism in my stable maps? For example, if I have a stable map with, let's say, irreducible domain, and this map is not generically injective. So, for example, it's 2 to 1. Let's suppose that 2 to 1. So I have, okay, for example, to be, if I have this map, this map is generically 2 to 1. So we can suppose that it's something like that. This is P1, and this is also P1. So we have that each fiber generically consists of 2 points. And what's the automorphism? It's the automorphism that switches the fiber. that send each point in the other point of the same fiber. So this map has an automorphism. So you have to think that when the map is not generically injective, then it's an automorphism. If it's generically injective, doesn't have automorphism generically. Why that? Because okay, suppose this does this image and it's injective. And an automorphism of this stable maps, what will do? So imagine I have a point that's sent to this point, and they have the same map. Okay, the same map should be sent this one, this point to this point. So an automorphism of this, since it's an automorphism of the map, not of the domain, must send this point here to the point that has the same image. So I have just one choice. Here I have two choices. I can leave the point where is it, or I can send to another point. Here I just one point because the image must be the same. So if it's injective, I don't have automorphism. And this is the subset parameterized free maps free of automorphism, and in general, the domain need to be reducible. This is the subset parameterizing maps with irreducible domain. They are very important. So we have an important theory, which is let's write just to be clear. Let X be smooth, projective, complex. Right. Normal. Okay, N0N, say X vector is locally because divided by finally, is a fine model space is non-singular. The non-singular fine moduli space. Oh, okay, of what we said before. It's a fine moduli space of the maps with reducible domain. Do you remember that this, with this we denoted the functor, and with this we denoted its coarse moduli space. This is a subset of this, and this itself is a fine moduli space for a functor. I don't know if you know what is a fine moduli space. Let's give the definition. Definition. A functor from the category of schemes to sets is represented by a scheme a functor from a scheme S2 family over S of fixed object. Moduli isomorphism. So, suppose you have a certain class of objects, which in our case are stable maps, and you define a functor that parameterizes this object. I mean, for each scheme, you send S, the scheme S, to all family over S of the object you want to parameterize. So this is a set, and you consider this set modulo isomorphism. This a functor F admits a fine moduli space M if as a functor F is isomorphic to the functor OM in the category of schemes with M. So this is M is a fine moduli space if F of S is equal to the homomorphism from S to M. The universal family is the family in Fn associated to the identity of M. What I mean? Okay, I have an isomorphism as a functor between this functor and OM schemes with respect to a fixed M, where M is a scheme. Then I can compute F at M. So I have F of M. This is the family of the set of all family over M. Modulo isomorphism. This is in bijection with homomorphism from M to M. In particular, here I have the identity of M. And since it's an object of this, it corresponds to an object of this. And this is what we call the universal family. Okay, and this is just to explain what is a fine moduli space. When we have a fine moduli space, a lot of things comes through because it's very, let's say, very easy to work because we have a parameterization, not all of the singular things we want to parameterize, but of family. This object parameterizes families. So we can do a lot of work. For example, an example of fine moduli space is the Grassmannian. And so for these reasons, intersection theory in the Grassmannian is so easy and works so well because it's a fine moduli space. But this is not a fine moduli space, it's just coarse. So some stuff work, some other stuff doesn't. Okay. Okay, now we have the open set that is without bar. Let's this theorem is very important. Let's give it a last theorem. Let's suppose that the X is still there. M bar 0M X beta, so all the space minus the open set so this is close because it's the complementary of the open set. This is the union. Okay, this is normal crossing divisor. What does it mean? It means that it's a pure dimensional divisor where we have many components and the components intersect itself in a transversal way, like the coordinate axis. And the lecture of today will be dedicated to this device. Let's see how we can knew it. Let's see. Okay. This divisor is called a boundary divisor. Okay. Boundary divisor of n bar 0 and x beta R of B A B equal 2 1. Okay, let's just try to give a justification. If this parameterized curve with irreducible domain, this parameterized curves with reducible domain. So all curves here have a reducible domain. So we have at least two components. Okay, we still have to, this must be stable. So let's remember, this must be stable. The degree of the image must be beta. So in these two components, we need to have all the market points. And each component must be mapped to some curve. At least it can be, or it can be contracted. So basically, this divisor parameterizes all possible combination of this object. So what I mean? A and B are disjoint set, and the union is all the maps. Beta 1 and beta 2 are homological class, and their sum is beta. Okay. So these are class of curves. If beta is equal to 0, beta 1 is equal to 0, or beta 2 is equal to 0, then A has at least, the cardinality of A is at least 2, and same for B. So, what this set with this condition corresponds? B, A, B, beta 1, beta 2 correspond to stable maps with two components. Okay. So let's say C, P1, Pn, mu is our stable maps. So C has two components. It may have more than two components, but for the moment, well, it's always connected. So if it has as many components we want, we always can suppose that it has two. Eventually, each one is not reducible. So C is the union CA, CB. Okay. Okay, CA, CB, where CA and CB are quasi-stable of genus D. I continue here. Okay, let's put a little bit of order. Okay, D corresponds to stable maps with two components. So this is the stable maps. First point, C equal to this union. These are the two components, where CA and CB are quasi-stable maps of genus 0. BI is in CI, CA, and PJ is in CB. for each I, A, and J, ED. Okay. Let's remember that since C of genus 0, the intersection of Ci and Cb must be just a point. Cannot be 2 points, because if I have a 2 point, I must have a loop. And a loop means genus 1. Maybe it's better to say this before. Just a little remark. Maths here in MAT, I can think as that this configuration its component is a P1 because if is of greater degree or if another type of curve the genus must be greater than 0. The domain can be quite complicated, but we don't care because we just want stability. As long as it's stable, it's okay. And there cannot be loops. So I cannot do something like this. Because if I have a loop, the genus is 1. So if this is the intersection point between CA and CB, it must be at least 1 point, because C by definition is connected. So I cannot have 2 irreducible components with the 0 intersection. Okay. CA A union this point, and mu the maps restricted to CA. This belongs to M0 cardinality of A plus 1 X beta 1. Okay, what does it mean? It means that I have 2 components. They need to be irreducible, but I don't care for now. CA and CB, where A is a set eventually empty of marks. So I have, for example, 1, 2, 4, 5. In beta, I have A is 1, 2, 4, 5. B is have the other market points. And the image of A of CA is a curve of class B1, and the image of CB is a curve of class B2. And the sum is okay. Why, if beta is equal to 0, then the cardinality of A must be at least 2? Because if this is contracted, it must be stable, so I need at least 3 marks. One is the intersection point with beta, so I need at least other 2 marks to have stability. Just that. And there is a way to describe this object.
Talvez eu primeiro parte de cima. Se quiseres mais, podes apagar a parte de cima. Or darf ich noch?
Because I want to give a justification of that. Okay. There is this description as a fiber product. Unit 0. So I have okay. I added one market point to A. So this market point is not between 1 and n. It's like n+1 and correspond to the intersection point here. So I can evaluate at that market point both spaces. And the fiber product is our device. So what this suggests us is that I can consider when I fix A, B, B1, B2 maps, several maps, one is CA, one is CD, both of genus 0, with maps that belongs to different sets, such that the union is the set between 1 to n, and I add, okay, this is image beta 1 and this is image beta 2. Then I add one additional market point to both curves, and I glue along this. And this is the result. And this is the boundary divisor of M bar, which is the most interesting divisor of.
So it's the union of all of those.
Yes, the union of all these spaces have the same dimension, which is one less the dimension of the entire space. They are normal crossing, and the union is called the boundary divisor of M bar. But each one is called also the boundary divisor. Okay. Now I think here the currency structure is because this divisor inside N bar look like other space N bar. So we have this Cartesian diagram. So if I know beta 1 and beta 2 and these moduli spaces, I can study this divisor that belongs to M bar with beta equal given by the sum. So here I have strictly less of okay, let's say I have a degree less than beta. Here also I have a degree less than beta that eventually can be 0. Here I have less marks. So I reduced both the degree and the mass, and I defined an element of M bar. So you have a recursive structure, which will be important later. We will see all the advances of this structure. So now we understood what does it mean this, and what I mean when I say generically better behavior. Well, in the first theorem, I give you the space M bar is purely of a very fixed dimension. Let's see an example. And let's see in the same example how Hilbert scheme behaves. So consider M00, P3, 3. So these are maps from P1 to P3, where the image is cubic. So a general point of this is a degree 3 curve, rational, and not containing to a P2. So this is a twisted cubits. And this space is of what dimension? We saw, so it's 4 times 3. So it's the main of kx times beta. So kx is 4 times 3, plus the dimension of x, that is 3, plus n, that is 0, minus 3, is 12. Correct? Yes. What's the Hilbert scheme of this type of curve? It's 3t plus 1, T3. And these are two components. One, it's of dimension 15, and the other one, which is not disjoint. The other one has dimension 12. So in this case, the Hilbert scheme behaves quite huge. We have a component of very large dimension, and it's not irreducible. Okay. Okay, so generic better be. But the fact that we don't parameterize curves, we parameterize maps as its own disadvantage. So if there are no questions from the public, I have give you some example, some real example. Okay. Let's take degree 1. So let's M0 and PS1. Okay. I must have B1 plus B2 equal to 1. So at least one of the two must be 0. So all divisors are of the form D, A, B, 1, 0. But this 1, 0 means degree 1 and degree 0. Okay. And the union of I and B is the number between 1 and n. So what happens if n is 0? This is S, yes, the dimension of this projective space. So here, no boundary divisor. I have no boundary divisor because I don't have enough marks. Because one component must be contracted because of degree 0. So I need 2 market points, but I have 0 market points. So no boundary divisor. The same of this. If I have just 1 mark, the same happens. No boundary divisor because I have just 1 mark. This space is the Grassmannian of lines in PS. So I don't know which notation to use. This means subvector space of dimension 2 inside the vector space of dimension s+1. And this same lines in the projective space PS. So this is the space which is a fine moduli space indeed. So no boundary divisor. Each one must be each map must be injective. So it's all stable maps here are automorphism free. The same of this, and if you remember from last lecture, we have a forgetful map which forget the marks, the only mark, and this is the universal family. This is a universal family over a mark. Okay, what happens is if I have two market points? What happens if I have this one? Yes. Not that okay, this example is true because I take PS. So this is the Grassmannian because X is PS. But if I change X, okay, I cannot mention the Grassmannian anymore. But what I said is the same. I mean, I have to be clear what is beta. You have to be sure that the beta is not sum of curves of less degree, but also this is more or less true. Okay. Now I can have a boundary divisor, which is D. Okay. CA. Okay, I want that CA is of degree 1. So I have 1. And if CA of degree 1, CB must be of degree 0. But if CB is of degree 0, I have 2 marks here. I must have at least 2 marks, but I have exactly 2 marks. So beta is 1, 2. And A is X. So no marks on CA, all marks 1 and 2 in C beta. And this is of degree 0. Image, a line, that is the image of C. Just a comment. It doesn't matter where I put these maps. So if I have something like this, this is not different. If they have the same image, this is not different because here I have P1. This P1 is contracted, so I don't care about its image. But since the automorphism of P1 is 3-dimensional, I have enough automorphisms to send this point here, and this point here. So this map and this map is isomorphic, and since I study the maps moduli isomorphism, this is exactly the same object. So I just say that I have one component with 2 marks without caring what these marks are. This doesn't matter. If I have an additional mark, then yes, but except for the moment. Okay. Now let's increase the degree. So instead of degree 1, let's consider degree 2. I have to clean the blackboard, so I have give some time so who is waiting to finish to write, because I'm going to cancel everything. Okay. A question? Oh.
Ask questions. Nobody is chatting.
Okay. I think it's a good point. Yes, sure. Okay, so I have 2 types of boundary divisors. A, B, 1, 1, or A, B, 2, 0. Okay, consider M bar 0, 0, yes, 2. I have no market point, so I cannot have contracted components. So B and 1, 1 is the only boundary divisor. So it's that one. That one. What happens if S equal to 1? So it parameterized maps from stable map from P1 to P1 of degree 2. So 2 to 1. So this is the type of maps, because this is our PS. And this is the domain. So what I have here is a parameterization of all maps like this. So basically what different, what makes 2 maps different if the choice of the image or of the ramification point. What happens if this ramification point coincides? That they have the boundary device. So it's also vice versa. If I have our PS that is P1 and I choose 2 points, I have a unique map where the ramification point is there. And so I have a one-to-one correspondence between pairs of point here and stable maps. So basically M0, 0, P1 true can be put in correspondence with the pair of P1. So it's true of P1. And when this is compact, so you have the case when these two coincide, and it's this one. I don't know if you know this, and this is isomorphic to P2. So this is P2. It's a general fact that the Hilbert scheme of n reduced points in P1 is isomorphic to the projective space. Okay. Now, when S is equal to 2, we have 4 types of maps. Okay. First of all, maps from irreducible domain with generically injective maps. So, who is here? We have so this automorphism free intersected with irreducible domain. And this, of course, is dense. It's the dimension of this. It's 5. It's equal to the dimension of all this space. Yes, this space is 5-dimensional when S is equal to 2. So we have these maps. We have the boundary divisor. So which is we have this is degree 1. This is also degree 1. So we have D and P1, 1, and 0, 1. This is isomorphic for what we saw before to this blue image. Okay. Okay. This is the Cartesian square. But we know that inside the Cartesian square, we have the diagonal, because these spaces are the same. Who is the diagonal? Okay, this is dimension 4. The diagonal is basically an embedding of this space here, which is three-dimensional. So diagonal is M0, 1, 1. Okay. What does it mean? It means pair of stable maps, one here and one here, which are the same. So they are the same image. So here in the diagonal, we have maps with the same image. Both of degree 1 with the same image. So, and this is degree dimension 3. So, who also here? Yeah. Okay, all this analysis is more or less the same in all the spaces. So we see this particular case, but in the other moduli spaces, we have the same object. We have reducible curves, and we can do the same analysis. So it's just an example that works now and forever. So we have also maps with irreducible domain, which are not injective. So it's this one. This is this space, let's say, let's call it Y, is this minus this. And again, how this space can be constructed? We have all the lines in P2. Since this is a 2-to-1 map, is uniformly defined by the image, by the branch point. So inside P2, which is really P2 dual, so the hyperplane in P2, we choose 2 points. So it's a P2 bundle. It's a P2 bundle over a Te-Grassmannian that defines P2. So it's 4-dimensional. So it's basically the choice of a line and 2 points over the line. Okay. This delta can be given as this intersection. 1, 1. Because when these 2 points coincide, I cannot have anymore a 2-to-1 map of this type, so I must have a reducible one, which are this here. There is for this particular space a very easy description, which is the following. You know that the conics in P2 are a projective space of dimension 5, no? I don't know if you are familiar with this. Are you?
Yeah. Well, yes, you just take the coefficients, which
yes,
projectivize.
So if I have conics, so these conics, conic in P2, I assign a point P5 because I have 6 coordinates, and this is uniquely this map is uniquely characterized by its image. This doesn't happen with this because in the image we have to distinguish the branch points, but here we have no branch points, so this space, this is also true for this. Since it's generically injective, the image is enough to uniquely find the stable map which that have that image. So this is the problem, this and this. So okay, let's write what I mean. If C mu does not in Y, then C mu is univocally defined by its image. Okay, modulo automorphism. So CMAFcIO is determined by the equation of its image. Okay. We have these conics. We have the double lines. So they are ix plus by plus c zeta squared. So inside P2, we take the equation of a line taken 2 times. This is the equation of, it's an equation of degree 2. It's a line taken 2 times. And here with this map, this is embedded in a surface isomorphic to P2. It's the Veronese surface simplified. So by what we say here, M bar 0, 0, P2, 2, minus y is isomorphic to what? Isomorphic to P5 minus V. And it can be proven that all M bar P2, 2 is isomorphic to the blue up of P5 along V. And this is called the space of complete conics. Because this is the space of conics, but not everyone can be done here. For example, we have, in the case of tangent conics, we have some bad thing. This is the space of complete conics, and there is this isomorphism, which I hope all this explanation helps you to clarify. Okay, I think the lecture of today that was like a large amount of examples to justify the space, why it's important. Next time we will do intersection theory on this space, and we'll start with Gromov-Witten invariants, and things will be less immediate, less easy to visualize. Okay. There are no questions. I think we can close now.
Yeah. Let me ask again. So thanks.
Thank you.
Let's answer some questions in the audience that's watching by streaming. Let us know. The question, let's see. So you said that M bar is, in case of X is convex, is a normal projective variety, which is a global quotient by a finite group. I mean, of a smooth projective variety by a finite group.
Yes.
Is that...
The singularities are
orbifold type.
Orbifold type. Yes.
So the question is, can you say something about that finite group, depending on those invariants that you
yeah, but the group is basically the group of this automorphism. So basically, we have singularities when we have curve with automorphism, which is the case. But since we are losing the automorphism, and the automorphism group is finite, that group is the group with quotient. It's a group of automorphism of a particular group. So in this case, it's theta 2.